So the next presentation is by my other friend and colleague, Professor Ruoxi Jia from Virginia Tech, who's going to talk about the most cost-effective deployment of AI systems. Ruoxi, all yours.
Thank you, Costas, for the introduction. Hello, everyone. Hi, everyone. My name is Ruoxi Jia. I'm an assistant professor at Virginia Tech. I run the Responsible Data Science Lab here, and my group has been spending a lot of time thinking about data quality, security, and privacy issues related to machine learning. And today, I'll be sharing with you some of the recent work that we have done to enable cost-effective deployment of AI systems through a better understanding of what is data that is worth to collect and use. So I want to start out with a bit of the story, starting from my PhD. So at the beginning of my PhD, I was working on this project of using machine learning to do indoor localization. Specifically in this project, we developed some software on a smartphone to measure the acoustic features of the room. And then we put together some training data set where the features are the acoustic signals that we collected from each room, and the labels are the room number. With this training data set, we built a machine learning model that can predict the room number based on the acoustic signals collected from the room. And we are able to achieve the accuracy about almost perfect. And we are really excited about this result. At about the same time, machine learning started to be utilized in some other applications in smart buildings, like anomaly detection, energy disaggregation, and thermal comfort prediction. Beyond machine learning, we have also seen a lot of success stories in object detection, understanding natural language, and playing games. So this is all seems like very exciting. And it seems that we have found some panacea to make progress in different domains. However, we really have a big problem. The problem is that it takes a lot of time and effort to set up a machine learning system. The core assumption behind all this successful machine learning system is that we have access to a large-scale, labeled, and high-quality data set. But in practice, gathering such data sets often takes a lot of time and cost. For instance, in my indoor localization project, what is under the hood is that we need to collect hundreds of sound samples in each possible location that we want to identify. Each of these example needs to be manually labeled with ground truth location. And sometimes due to the failure of software and hardware, there are some samples that are low quality. And in that case, we need to manually remove the low quality examples to ensure the good prediction performance. Look at some other applications of machine learning like computer vision. To train a good machine learning model in computer vision, it takes millions of high quality labeled images. And that means thousands of human hours. And for game playing, to learn a good Go player, we need to learn from millions of games. And to successfully translate it between different languages, the model needs to be trained on more text than a human could read in a lifetime. So the challenges for deploying machine learning in a cost-effective fashion is really that we need a large, labeled, and high-quality data set. But in reality, collecting a labeled data set is expensive and slow. For instance, in image recognition, it requires millions of data sets, so the human labeler needs to go through millions of data and figure out what is object in the data. Worse yet, in some applications, even labeling one example is already very expensive, especially in those applications that require high skills like medical diagnosis. In addition, because to control the cost, sometimes we can't be too picky about our data sources, and hence the quality of data is oftentimes low. For instance, data might be collected from some cheap sensors or low security sensors, and the data from those sensors might contain a lot of noise or suffer from security attacks. Another example is that your data is labeled by some low-skilled workers, and in that case, the label might be wrong. So there are many reasons the data might be low quality. Today, towards this goal of cost-effective deployment of AI system, I want to talk about two things. One is how to reduce labeling cost and time. The other thing that I want to talk about is how to detect various types of bad data. So let me start with talking about some work that we have done to address the first question. Let me start with this conventional machine learning pipeline. So in conventional machine pipeline, we have a large unlabeled data, and we randomly select a subset from this unlabeled data and give them to a human labeler to label them. For instance, we might get some images labeled with bull, some other images labeled with dog. And then we will turn these labeled images over to the machine learning algorithm, and the algorithm will try to learn some function that mimic the human labeling process. So this is often called passive machine learning in the sense that the labeled data are passively given to the learning algorithm, and the learning algorithm doesn't really have choice to choose what are the data that it wants to learn. And we know that the limitation of this conventional machine learning is that it requires a lot of labeled data. So there has been a lot of interest and active research in how to reduce labeled samples of machine learning pipeline. And the main solution is so-called active machine learning. The goal of active machine learning is to automatically select most informative data for labeling. So we still start from unlabeled data sets, but instead of randomly selecting some data to be labeled, we will introduce some algorithmic components into the algorithm, which is this data selection. The data selection will strategically select the data and send them to the human labelers to get them labeled. For instance, one simple strategy to select unlabeled data is to select those data that are most confusing, to select those data that the machine learning model is not yet certain about. And those data are often near the decision boundary. And the idea is that the hope is that if we can figure out the most confusing example, then the machine learning model will be more effectively learn the prediction rule. So after the labeler labels those data, we will use those labeled data to update the machine learning model. And then the machine learning model, the newly updated machine learning model will be used to inform the data selection strategy. For instance, back to this uncertainty example, to find the most uncertain example, we need to know the decision boundary. So we'll basically look at the current machine learning model, decide the decision boundary, and find the most uncertain sample, and then combine it, use it to train the machine learning model again, and then update the decision boundary, find the newest, most uncertain example. So active machine learning often runs in iterations, and it is done sequentially in the sense that the data selected in current rounds depend on all the data that are selected in the previous rounds. And in order for active machine learning methods to be effective, it requires many rounds of interaction with the data labeler. Okay. So the side effect of this multi-round nature of active learning method is that they often end up being very slow. So one reason is that common labeling platforms do not really support a timely interaction with data annotators. For instance, one common labeling platform is Amazon Mechanical Turk. In that platform, of course, we can actively acquire the feedback from the data labelers, but it often takes time before our active queries are answered by the labelers on the marketplace. So effectively, if we want to accomplish the labeling in a certain time frame, this limits the number of rounds that we can interact with data annotator. Another reason that active learning is slow is that because active learning is sequential, so the labeling process cannot be parallelized. We can't really increase the labeling efficiency by having a large pool of data labelers and ask them to label at the same time. So parallelization is not a solution if you have active learning. So this motivates us to look at a new setting of active learning, which is one-round active learning. The goal of one-round active learning is to select the most informative points from unlabeled data sets, but query their labels all at once. We want to avoid doing this active learning sequentially. So one important advantage of one-round active learning is that the queries can be labeled completely in parallel. So that means high throughput and low cost. Another important advantage of one-round active learning is that it does not require any specialized platform to support a timely interaction with the data labeler. So this can be used in tandem with many existing labeling platforms like Amazon Botanical Turk, or outsourcing the data labeling to some companies. So then we start to think about how to approach the problem of one-round active learning. So our first try is to, well, we already know how to do multi-rounds active learning. There are many existing work of that. So how about we just limit the number of rounds in the best existing active learning approaches? But that doesn't work. Why? So the first reason is that existing active learning approaches use some not very effective selection criteria. For instance, I have mentioned this criteria of labeling most uncertain data. But remember, what is our end goal? Our end goal is to select the data that can give us the highest model performance. This uncertainty, of course, it is correlated with model performance, but it is only weakly correlated. It is not directly aligned with our end goal of improving model performance. And secondly, this existing selection criteria are computed from the model trained on the available label data. If we have limited rounds, it means that we have limited label data. Therefore, the model in the early rounds tends to be very erroneous, and the selection criteria computed from the models also tends to be erroneous and unreliable. So our approach to this problem is to say, well, existing work only use some unreliable criteria to select data. So how about we just directly estimate the performance of the select data and find the data that can achieve highest model performance. So then the question is that how can we evaluate model performance for given unlabeled data sets? So if we can efficiently evaluate model performance for any given unlabeled data set, then we can just find out the unlabeled data set that leads to the highest model performance. But to evaluate model performance for given unlabeled data sets, we need to go through this pipeline. We need to first get it annotated and then train a model on the labeled data set and then evaluate the performance of the model and give some score like model performance. So we need to go through this entire pipeline in order to evaluate the performance for given unlabeled data. So in abstractly, we can think of this pipeline as a function that map a unlabeled data set to a score that describes how useful this unlabeled data set is. And we call this function data utility function because this function output a score that describes how useful the data is. So with this notion of data utility function, then we can formulate active learning problem as a problem of finding a data set that maximizing the output of data utility function. So now it seems that we have a very clean formulation of active learning, which is just a maximization problem of data utility function. But the problem is that this data utility function is really expensive to evaluate. So to evaluate this function at even a single subset requires us to get this set annotated and then train a machine learning model on this subset. So it's really expensive to evaluate this function, let alone optimizing this function. So our main idea is to use a data-driven approach to approximate this data utility function. Well, we know that it is very expensive to evaluate. How about we approximate this function with a neural network? So if we can find a neural network that closely mimics the data utility function, then we can directly estimate the performance of any unlabeled data set by feeding the data set as the input of the neural network and then get the output. So once we have this neural network, then evaluating, estimating the performance of a data set will be very efficient. And then active learning can be done by, instead of maximizing the data utility function, we're maximizing this machine learning model, this neural network that approximates data utility function. Okay, so this is the main framework of doing OneRound active learning. So we first construct some training data to learn this model that approximates data utility function. And then with this data set, we learn the data utility model. We call this neural network a data utility model. And then the active learning can be done by selecting the unlabeled data set that maximize the data utility. So now it seems that we have a very clean pipeline to do OneRound active learning. But we really have one problem. The problem is that it is very expensive to construct the training set to learn this data utility model. Remember, what is the training data? The training data is a pair of consisted of many pairs of input and output of the model. So the input of this model is unlabeled data set, and the output of this model is a score. But to calculate the score associated with a data set, we need to label the data set and train on this data set. So it means that to acquire each of a training sample, we need to retrain the model for once, which will be expensive. And if we want to collect n training samples to train this data utility model, we need to retrain our downstream machine learning model for n times. So the total computational complexity for constructing this training data set is the number of training samples that we need to approximate this data utility function accurately times the time it takes to train a downstream machine learning model. Okay, so here are some our key observations to address the computational issues associated with data utility learning. So previously, we have seen that the computational complexity depends on two factors. One is that how many samples that we need to approximate data utility function accurately. The other is what is the time to retrain the downstream machine learning model. So one interesting finding that we got is that although retraining a large model might be very time consuming, but we found that actually the utility of a large model is correlated with the utility of a small model. So what does this figure show? So each dot is a different data subset, and x-axis represents the model performance of this subset to train a small logistic regression model, and the y-axis is the performance that we get to use this data set to train a large model. And we can see that although the performance that we get from small model is oftentimes lower than the large model, but they are positively correlated with each other. So this implies that we can actually use some small efficient proxy model to perform efficient retraining instead of using the large model. And in terms of the number of samples, we found that, well, although it's to learn some general functions, it takes many, many samples, but actually data utility function is a special function. It is special in the sense that we found that it has this diminishing return property. More specifically, as we increase the training size, the increment of accuracy saturate. So in optimization literature, it is called some modularity. So in the past literature, it has been proved that if the function is submodular or it has this diminishing return property, then it can be learned with small samples. So together, combining these two observations, we know that to reduce downstream model training time, we can replace the downstream model with a small proxy model. And the submodularity guarantees that we don't really retrain the model for many, many times to approximate the data function accurately. So together with these observations, we actually found that we can do data utility learning very efficiently. So this is the performance of OneRound active learning if we use this approach of learning a data utility function and then optimizing it. Our baseline is, because we are the first to study active learning in this setting, we don't really have baseline that directly compare with our method. So our baseline here is to limit the state-of-the-art multi-round active learning method to one round. It is a very natural baseline. So our method is shown in the blue line. And we study data selection in two settings. One is in one setting, we have data sets that is mixture of noisy data and clean data. In another setting, the data set is a mixture, is a really unbalanced data set, meaning that some class has significantly more data points than other classes. So ideally, in the first setting, we want to select clean data, and in the second setting, we want to select a class balanced data set. So you can see that as x-axis is the number of data points that we selected. Ideally, we want to see the model performance grows very quickly if we select more data. So that's exactly what we have seen for our method, and it achieves large improvement over the existing work. A quick note is that the brown line is optimal method, so it shows the theoretical optimal of the selection performance, but it is not realizable. So it is just shown here to see how well we do towards the theoretical optimal. So let's zoom into some of the selected data. So here is the rank of the data being selected. We can see that the early data that we select tends to be clean, and later data tends to be very noisy. And this is experiment done on the face recognition data set. You can see that the early data contains a complete face, whereas the later data contains either some irrelevant features or corrupted face. And this is the results selecting from a digit data set. So the last 10 digits you can see contains a lot of 1. That is because this data set is unbalanced. It has more ones than other digits. So that's why the last image contains a lot of 1, because it leaves those redundant ones to the last round. All right. So there are some other fundamental questions related to data utility learning, which I don't have time to dive into. The first question is that in this talk, we kind of use neural network as a default model to approximate data utility function, but is it really a reasonable choice? So in this paper, we kind of show that neural network is indeed a good model to approximate this function. And another question is that we give some theoretical justification of the data efficiency of data utility learning. All right, so let me talk about the second question, how to detect various types of bad data. In reality, data, oftentimes we have low quality data. And given the budget or cost constraints, the data quality is even lower. And the data is bad for many reasons. Some of the data might be mislabeled. Some of the data might be outliers or contain lots of noise due to sensor failures. Some data might be biased towards certain population. And if we directly train a model on biased data set, we get a model that inherits the same bias from the data. And some of the data might suffer from security attacks. So data poisoning attack is a specific attack targeted at the training data set. Due to the diversity of data issues, there is an urgent need of achieving general robustness to bad data of different types or even unknown types. However, in existing work, detecting bad data is a long-standing problem, but most of existing work can only achieve specialized robustness to bad data of certain types. So they only focus on achieving robustness to specific types of bad data. There are two lines of work that can potentially achieve general robustness. One is differential privacy. It is originally proposed to ensuring people's privacy, but then people find that actually, learn machine learning model with differential privacy can also improve robustness. So the idea of differential privacy is to limit the impact of individual data points on the model. But the side effect of differential privacy is that it provides this, it limits the impact of individual data points in an undifferentiated manner. So it doesn't really differentiate from good data and bad data. So it also limits impact of good data. And as a result, the performance of training a model with differential privacy is really low. Another approach that can potentially achieve general robustness is so-called data valuation-based approaches. The idea is first to measure the importance of each training data to the training processes, and then rank the data based on their importance and filter out the data points with low importance. But the limitation is that empirically it is found such approaches suffer from a lot of variance in terms of their performance. So our key insight to achieve general robustness is that although different data are bad for different reasons, but there is a commonality between bad data of all types is that they all contribute very little to achieving good model performance. So if there is a data that can contribute positively to machine learning, then we might just as well keep the data in the training set, and they won't be regarded as bad data. So therefore, it motivates us to detect bad data by looking at the performance of the associated with the data. So based on this intuition, a very naive way of removing bad data is to exclusively enumerate all possible subsets of a training data set, and then find the subsets with highest model performance. So we extract a subset from the training set, we evaluate the model performance by training on the subset, and then evaluate the model performance against some validation data. But again, we have seen the same problem, which is it's very expensive to even evaluating the model performance for one single subset, let alone many possible subsets and then find the best subset. So we kind of use the same idea as before. We try to use a parametric function to approximate this very inefficient pipeline. And once we can find a neural network that can approximate this pipeline, then we can directly solving the bad data removal problem by optimizing this function's output with respect to the subset in the input. Okay, so here is the evaluation of using this data utility learning-based approach to detect bad data. And we evaluated on various types of bad data issues, including mislabel and 2 types of security attacks, poisoning attacks, backdoor attacks, noisy features, biased data, and as well as a scenario where there are a lot of redundant data. So in all these cases, we want to remove the data and remove the bad data to maintain the good model performance. So here I showcase the performance of our method in several, in some of the settings, security attacks and noisy feature and mislabel. So on the x-axis is the number of data points that are selected by each algorithm, and the y-axis is among those selected data points, how many of them are indeed bad data. So the higher detection rates, the better. And our method is this data sifter, which is denoted by the red line. And you can see that in most of the cases, our method can achieve a large margin improvement over the state of the art. All right, so to conclude, I have talked about our work towards addressing 2 questions. One is how to reduce labeling costs and time. The other is how to detect various types of bad data and achieve general robustness. So the takeaway from the first work is that traditional active learning in practice, due to their multi-round nature, they tend to be very slow. So to make sure that active learning is useful in practice, we really need to consider a setting where we want to use active learning with limited rounds. And we can do it using the approach that we proposed based on data utility learning and optimization. And the takeaway from the second question is that although bad data can be bad for many different reasons, but good data and bad data can be robustly differentiated based on their utility. That's all I want to talk about, and I'm happy to take any questions from the audience.
Thank you very much, Ruoxi, for this presentation. I have a question for the very beginning, maybe a naive one. When you do the assignment to people to actually do the labeling, that assumes that you have at least some data labeled to have some initial model, and that's a general question. What do you do with the data that is completely unlabeled?
Right, so that's a great question. So that's the underlying assumption of the work that I presented. But recently we have done another work that's completely be able to remove that assumption. So let me maybe give you the high-level idea. So the idea is that if we do not have some initial label data, then it seems that we have no ways of designing a data selection strategy. However, in many scenarios, although we do not have label data from the particular task that we are interested in, we might have some label data from a related task. So we leverage this idea of domain adaptation. We try to learn a data selection strategy from some related data from related domain, and then transfer that strategy to the task that we are interested in.
Great. There is a question by Clayton on the chat. You might want to look at it, but also I would like to open it to the audience. Please raise your hand or post questions on the chat for Ruoxi.
Yeah, so maybe let me first address Clayton's question. We found bad data is a big deal in the competition, as this technique is essentially like a type of anomaly detection. Any other comments on the practical use of these techniques beyond processing training data? So the first question is that, is it type of anomaly detection? Well, in some sense, yes, we are trying to detect anomaly, but the problem, but I guess the unique attribute of our work is that we can detect anomalies that are caused by different reasons. So previous work can only detect specific types of anomaly. For instance, they can detect some out of distribution data, but they may not have the ability to detect some data triggered by security attacks. So they kind of all suffer from the variety of anomalies that can be detected. But this approach is more kind of a way to comprehensively detect different types of anomaly. And the second question is that any comments on the practical use of these techniques beyond processing training data? There are a couple of, the general idea of this data utility learning can be used in many ways. So like I said, so essentially data utility learning allow you to estimate the performance associated with a data set efficiently. So you can imagine maybe you can use, so in this talk, I have talked about two use cases. One is to do active learning, reduce annotation costs. The other is to select training data. And you can even think about, once you have this data utility function, you can synthesize some useful data, right? You know what, you essentially learned a mapping that can tell you what type of data is useful to train machine learning tasks. If you have this function, then you can maybe do some data synthesis to synthesize new data that are useful to accomplish a machine learning task. That is also something that we have been actively looking at.